All right. So thank you for joining us. So we're just going to go over real quick what the NASA Space Apps Challenge is, a little bit about what you're going to be doing, and just a little bit about kind of how cool it is and how we're grateful we are that you took the time to join us today. So what the NASA Space Apps Challenge is the largest annual hackathon in the world, and it's put on by NASA and a bunch of other space agencies. Uh, and what's really cool about it is that anyone and everyone can participate in this because of NASA's open source software and open source data. They're encouraging people to jump into science and experience STEM for themselves. Um, Now, if you haven't yet registered, um, please go ahead and register by going to www.spaceappschallenge.com slash and then or .org, my bad. And you can register, and then after you register, be sure to choose Logan, USA as your local event. And after that, you can choose a team. Now, choosing a team can be tricky sometimes, but when you do choose a team, make sure that you're choosing friends, make sure that you're choosing um, people that you know that you can work well with and that there won't be any conflicts with. But either way, it'll be a fun time and it'll all be a good learning experience for sure. Now, as we continue, I'd like to talk a little bit about how we're going to be doing things today. So, what we're going to do is we're going to have a local award. Um, we're going to have a local award that we're going to be giving out, and with that, we're going to um, we're going to have people give us their proposals for their projects. Not yet a complete project because you'll have until midnight tomorrow to turn those in, but just a proposal, and we're going to give that proposal to everyone in the form of a survey, and everyone will get to choose which is the best proposal, and that proposal will get um, the People's Choice Award, and then there will also be two other awards: the best use of science and the best use of engineering, and these the people who win awards will be given certificates saying that they won the People's Choice Award or the Best Use of Science Award or whichever award applies. And the deadline to have that turned in by will be 4 o'clock tomorrow. Now to turn that in, there will be a survey that will be emailed to all the participants who have registered for this event and chosen Logan to be their local event. So in order to submit it, simply respond to that email and upload your project there. And the same thing for answering the survey to pick whichever one was the best one. Now, the awards will be the closing ceremony and the local award ceremony will be presented at 8 o'clock tonight, or not tonight, next tomorrow night. And that's where we will do a bit of a closing, discuss some of the things that have been learned here, as well as um, just going over the awards that people have earned, such as the People's Choice Award and the Best Use of Science, Best Use of Engineering. And So for now, with most of the logistics out of the way, I'd like to introduce uh, our guest, Bella Nielsen, with the gas team, to who would like to discuss some of her work and some of the really cool things that she's been working on. So Bella, you now have the floor.
Thanks, Gavin. Hello, everyone. So, as Gavin said, my name's Bella, and I am the outreach director here on the gas team. So, I'm kind of in charge of all like our little, a lot of things, getting the community involved and getting students involved. And so today I'm just going to be going through kind of some of the different projects that we worked on the gas team and a little bit about how that's been beneficial and how that relates to challenges like this. Okay. Okay, so that's kind of a little bit about myself. I'm currently a senior in mechanical engineering with an aerospace emphasis. And as I said, I'm the outreach director, and this is my fourth year on the gas team. I've been able to work on a couple different projects on the gas team before doing outreach. I was able to work with our mechanical team, work on the development of a thermal vacuum chamber, and I've also been able to be involved with a lot of our proposals that we've written, which I'll discuss a little bit more later. I've also been able to be a three-time intern with Northrop Grumman in their rocket motor test area here in Promontory, Utah. And it's been a great experience to get different experience in the industry, as well as to see how much I've been able to learn on the gas team and learning actual engineering skills. So, start off, what is the gas team? We're the Getaway Special Student Satellite Team, Utah State. We're the ones putting this event on, and we are a student satellite team, and we're focused on building CubeSats. A big benefit of our team is we're completely undergraduate run, so we're making all of the decisions, which is a really unique aspect. A lot of other satellite teams we've talked to, while they do have a lot of students on them, there's a lot of influence and work done by the principal investigator. So being able to be on this team and make all the decisions as a student is really meaningful. There's a little bit of history. The Getaway Special Program actually started in 1976 with NASA's Getaway Special Program. This was a program where you could pay like $10,000 and you could have a 50-gallon drum and fly experiments on the space shuttle. USU was actually the first university to send a gas payload through Gilmore. He's shown in some of these pictures on the bottom here. And throughout that program, which lasted from the beginning of the shuttle to 2003 after the Columbia disaster, Utah State flew 10 gas cans, all with multiple student experiments. After Columbia, the team couldn't do get the gas cans anymore, so they transitioned to bomb comet flights and high altitude balloon flights, and eventually came to CubeSats. The first CubeSat that the gas team built was GasPax, or the Getaway Special Passive Attitude Control Satellite. This satellite was started and proposed to NASA through that CubeSat launch initiative in late 2013. It was completed in August of 21 with the launch to the International Space Station on a SpaceX resupply mission in December of 21, and then deployed in January of 22. Then the satellite has mission space, re-entering in May of about 2022. So a little bit more about NASA's CubeSat Launch Initiative. So this is a program through NASA's Launch Services Program at Kennedy Space Center, and it provides educational institutions and nonprofits with a ride to space. So this will, once you submit the proposal and you're accepted, it will pay entirely for launch, and this can go to three different types of orbits, such as low Earth orbit, sun synchronous orbit, or non-sun synchronous orbit. And with this program, it also work with a third party for integration, such as nanoracks. So on gas packs, how that worked is we delivered the satellite to nanoracks in Houston when the satellite was complete. It was integrated within the deployer, and then it was taken to Kennedy, integrated with the ISS. Well, then it was integrated with the ISS resupply mission, and then was eventually deployed from the International Space Station. So for the gas packs, the primary mission objective was to deploy and photograph an inflatable meter-long boom. This is known as the air boom. And then the secondary objective was to measure and observe how the inflatable boom could passively stabilize the satellite. So just a little bit more about the payload. This was a meter-long inflatable boom. It was sealed here on Earth with about 2.2 psi of air. And on Earth, that's relatively low, so the boom was still flexible and able to be folded into the satellite. But then once in space and the boom could be deployed, it was able to inflate because there's very, very little pressure in space. So that pressure difference caused the boom to inflate. Then because the boom was dragging behind the satellite, as shown in these pictures here, the boom helped passively stabilize the satellite along the velocity vector using the little bit of drag that is in low Earth orbit because there is still a little bit of atmosphere. So there's enough that there was drag force to keep the satellite from completely tumbling all over the place because of the air boom. So this is just a little video of how that works. So this is in our vacuum tube. You can see there the burn wires are cut and then the boom was able to inflate and pop out of the payload container. So this took a lot. Took a lot of development, and so these are just some pictures of the different development with the electrical board, with the payload, software, and just all the different systems that went into the satellite. And then these are some pictures of delivery and launch. You can see here in your top left, this is a picture of the deployer that the nanoracks deployer that the satellite was in. And then these pictures along the bottom here are a bunch of our team members actually went to the launch in Kennedy to see the satellite launch. And so these are some pictures from that launch as well as around some of the facilities. Then this is a video. So to deploy the satellite, they take that nanoracks deployer and they put it on the end of the Canada arm, and then they shoot it out. So here's a video of that deployment. We are the gas packs is the bigger satellite. There's also another satellite, I think phase 2 is its name. So 1/3 U. And so they would put multiple satellites within the deployer. And here's another picture of the satellite coming past the solar panels on the ISS. And you can kind of see the deployer in the top right corner. And another picture. Ours is the bigger square satellite in the middle. And so once the satellite deployed, it has to be shut off for about 30 minutes to make sure that nothing happens too close to the International Space Station. And so once it turns on, it kicks on. And at this point, the team was together. We had watched the deployment. We were waiting for, and we saw deploy. We're waiting for that 30 minutes, and then it was time to see if it was working. Our ground stations, we are part of a network known as SatNOX. So it's a amateur radio organization, ground station network that is across the whole country. So we are actually able to be looking for our satellite and seeing if we could hear it from ground stations all over the world. And big thing we were looking for was this beacon, which is actually part of our school song here at Utah State. And so that was and we got that over a ground station in Tokyo. So that was the first sign of life, and the satellite was working, the antenna was on, and that was an amazing thing to hear. And we got that about 40 minutes after it deployed from the ISS. Later that next day, so this was pretty early in the morning, that night, we were able to get our first picture down from gas rats and gas packs, and you can see that here. the boom had and we it was for confirmation that the boom had deployed. So within 24 hours, the primary mission objective had been achieved. The boom was deployed, and they were able to get a picture down. Later that day, we were able to get a picture in the daytime, so we could actually see the boom in space. And it was great to know that like the satellite worked. And throughout the course of the mission, we were able to get some more awesome pictures down. This one's cool. I think this one's over Montana, Idaho somewhere. And then this one's favorite. You got the curve of the Earth in there, and it's awesome just to see like this is in space. And so overall, Gas Packs was a complete mission success, and it did a lot of awesome firsts. The Gas Packs was the first CubeSat that was completely built by undergraduates. We had a faculty advisor, but it's mostly they're kind of making sure we didn't spend money where they were supposed to. So it's really unique to have it completely built by undergraduate students. Gas Packs also completed the primary objective in 18 hours, as I was mentioning earlier, with the deployment of the inflatable boom. Gaspacks was also the first satellite to use a Raspberry Pi Zero as a flight computer. Raspberry Pi Zeros has been used as kind of payload computers or secondary computers, but Gaspacks was the first to use it as the main computer, which reduced the flight costs from about $10,000 to about 10, which is a big, big cost reduction. It was also able to demonstrate that the boom could inflate and demonstrate that technology. Over the course of the mission, we were also able to downlink 9 images. Those were just some of the ones I was showing before. And they're just different parts of space, and you're able to get some high quality and some low quality images. Throughout the mission, we were also able to interact with amateur operators all over the world using that SatNOGS network, because we were continually using other ground stations in order to talk to gas packs or get more data and to get more pictures down. We're also able to create an open source and robust software platform for satellites. So the code for gas packs was completely written by the gas team, and that was a unique aspect of the mission. Gaspacks was also able to download pictures despite losing 3 of the 5 solar panels over the course of the mission. This was due to a complication with one of the customer off-the-shelf components. And because of this power loss, it meant that Gaspacks was consistently solar cycling. And so it made it difficult to get down data. And that's why having the SatNOGS network was very, very useful, because we could take more advantage of those times when the satellite was on. Satellite was also able to survive the largest solar flare since 2017. This was like within the first couple weeks of the mission, there's a big solar flare, and I then be able to survive, and the computer and electronics were able to keep working despite that. So now that Gaspacks is wrapped up, completed mission success, we are now working on a new satellite called GasRats. This is the Getaway Special Radio and Antenna Transparency Satellite. So this one is going to be a 3U satellite, so about 3 times the size of Gaspacks, so 10 by 10 by 30 centimeters. And this will be testing a transparent patch antenna that can be mounted on the solar panel. GasRats will also feature a unique educational outreach program, and the plan is to have the satellite completed by 2026 and will be launched through NASA's CSLI program again. So it was a little bit of a long road to get to CSLI. We applied in 2022, rejected, so we reapplied in 2023, applied the feedback we received, and we were able to get it. So this is a picture here of the announcement of us getting CSLI. So that is going to be our rides for space for GasRats. We're going to be going through doing a ride share through NASA CSLI again. And so our payload, as I mentioned before, is the transparent patch antenna. So this is an optically transparent solar panel integrated S-band patch antenna. So having a patch antenna on CubeSats is desirable because it features higher data rates, so you can get more data down. Now, this is something that would have been helpful in gas packs when we were power cycling so much. So being able to get more data down in the same amount of time would have been very beneficial. However, on CubeSats, transparent patch antennas are usually put on the satellite instead of a solar panel. And when you don't have a lot of surface area, that can significantly decrease the power generation. Therefore, by making the antenna optically transparent, the antenna can be mounted on top of the solar panel, and so there's only about a 10% reduction in power output from the satellite from the solar panel in that location instead of 100%. And so this is able to make the most use out of that space, providing higher communications while still preserving power production. The antenna is made by printing silver nitrate ink onto the thin polyimide film. So this is meant to allow the to create a mesh pattern that allows sunlight to come through. And a film is used because by tensioning it, then it can stay rigid but not break during the vibrations of launch. The satellite also must be low mass and low profile, so it's another way where the silver nitrate ink printed on the thin polyimide film is beneficial. Patch antennas, while they do feature higher data rates, are directional, so we have to be able to point our satellite. And this is going to be done with our attitude, determination, and control system. This is going to be made with 3-axis magnetorquer only control. Magnetorquers work by exerting small torques base uh, by exerting small torques on by interacting with Earth's magnetic field. So the all my different magnetic fields will be with the magnetorquers, and those will interact with Earth's magnetic field. And because there's drag or gravity or gravitational pull influence as you would have on Earth, those small magnetic torques, those small torques caused by the magnets, are able to turn the satellite and orient it in the direction that we need. The attitude or orientation of the satellite is going to be determined using sun sensors and a magnetometer, so seeing where the satellite is pointed in relation to the sun and that magnetic field. However, using sun sensors is only useful if you see the sun. So when we're in a low Earth orbit, so we'll be eclipsing the sun. The sun will be the satellite will be in eclipse for about half the order. So there needs to be a way to determine the attitude when those sun sensors aren't able to provide sun vector data. So this can be done through Kalman filtering, which is kind of propagating the orbit, as well as other sensors. Another unique aspect of the Gas Rats mission is that the software is going to be using the F Prime software framework. So this is an open source software framework that is made by the Jet Propulsion Laboratory and NASA. This is easy to use and integrate. It is mostly written in C++ and compiles on the Raspberry Pi, which is useful because our team was planning on using a Raspberry Pi again as the main flight computer after it was proven on gas packs. F Prime is also super cool because not only is it made by JPL, but it was the software framework that was used on Ingenuity, the Mars helicopter. So it's kind of fun to know that we're using the same software as the Mars helicopter, and we've also been able to actually have contact and go to workshops at JPL to learn more about the software and interact with the developers of the F Prime software framework. With our satellite, we also have to have ground stations so we can talk to it. For the gas packs mission, we are going to be having 2 ground stations, an S-band ground station, which will be used with the transparent patch antenna, as well as a UHF ground station. Because the transparent patch antenna is a technology demonstration, we will also be having a UHF antenna to ensure that we can for sure talk to the satellite in case something goes wrong with the S-band antenna. We're also only planning on transmitting from the satellite to the ground station with the transparent patch antenna, so any uplink will need to take place with the UHF ground station, so sending any commands to the satellite. We currently have a UHF ground station built. It's on one of our lab buildings, and we are working on putting together an S-band ground station. And the unique thing for the Gas Rats program, and this is a lot of what I'm involved in, is our Bring Utah Students to Space program. So this is going to be a unique opportunity for K through 12 students all throughout Utah to have their names flown on the bus payload. And this is just an opportunity for them to interact directly with gas rats into space and hopefully inspire the next generation to go into space and pursue STEM. And also just to know that they can do it. They can go build satellites or go work on rockets and that space is out there. Overall, I've been able to learn a lot of different things from the gas team and a lot of like professional skills. So I was able to see a lot of different disciplines of energy engineering. Like I said, I'm a mechanical engineer, but I've been able to expose to a lot of different aspects of electrical engineering through red satellite systems as well as systems engineering. So being able to see the different requirements and the all the different planning that goes into preparing a mission and also proposal writing. I've also just been able to gain hands-on engineering experience. So putting projects together, design, seeing what happens when you face problems and having to readjust. And as a team lead and working with different groups of I've also been able to develop skills in communication, teamwork, and leadership, and is able to learn a lot more about what it looks like to actually be designing a project and facing problems. And these learning these lessons has been really helpful with my internships because I've had an idea of like, okay, this is the things you have to consider when you're doing an engineering project, and being able to take some of those experiences with industry and take it to Northrop Grumman and kind of be able to see like, okay, this is how you should interact with people. This is like how to take accountability. And overall, it's been very, very beneficial to be able to go and get skills and also just to try things out and to see what's out there. So my main takeaway is whatever you're doing, just get involved in something and learn. So whether that's joining a club or attending events like this challenge where you're going and trying and trying out these challenges using open source data and just seeing what you like, what you want to do, and also just applying yourself. It's a great opportunity to is gain different skills and just broaden your experiences. So that's just an overview of some of the projects of the gas team and benefits of kind of joining challenges like this. Are there any questions? Okay, in that case, I'll turn it back to you, Gavin. Thank you.
All right, thank you, Bella. So now I just wanted to close out and just say thank you for coming and thank you for participating in the NASA Space Apps Challenge. Um, it really is great to work with actual open data that that NASA has provided, and being able to work on these challenges to engage in science, technology, engineering, art, and math. It really is a great way to learn and to maybe apply the things that we're learning and just to have fun. So I hope you have a great time here at the NASA Space Apps Challenge, and I wish you the best of luck. And remember that we'll see you again tomorrow night at 8 o'clock p.m. for the closing social. And if you'd like to have your local project proposal submission turned in to be judged and um, to be included in our survey for um, the People's Choice Award, make sure to have that in by 4 o'clock p.m. tomorrow. And again, that will be the link to do that will be sent in an email to anyone who's registered for this local event on the NASA Space Apps Challenge website, which again is spaceappschallenge.org. Um, Thanks again, and best of luck with your best of luck with the hackathon.